Hello, everybody. My name is Miao. I'm a PhD student from Karlsruhe Institute of Technology. I'm very happy to present this work for the optimized soft-aided decoding of OFEC and staircase codes to you. And this is a joint work with our former student Lucas Hub and my supervisor. And we have just presented this at ECOC 2022 in Frankfurt. So I will start the presentation with some high-level background and motivation. The topic is product-like codes, which are suitable code construction for high throughput systems because they have a low complexity decoding algorithm, which makes them able to handle very high data rate. The example codes includes product codes, braided codes, OFEC codes, staircase code, and zipper codes. They are widely used in different systems, most likely in the optical communication systems. And what we are specifically interested in this work is the iterative message passing decoding. We want to improve it. And why do we want to do this? It's because when we look at the two existing options of decoding such codes, we see that they both have their drawbacks. For example, if we look at the soft decision decoding, the SCD, or turbo product decoding, or more, some people call it Chase-Pindia decoding, it gives us very good decoding performance. But it also has the problem that it's quite high computational complexity, and also it requires soft message passing, and this causes very high internal decoder data flow. And when we have very high data rate, it may be challenging to implement the Chase-Pindia decoding. And then we also have the hard decision decoding, which is also called the iterative bounded distance decoding, the IBDD. The advantage is that we will have very low complexity and internal decoder data flow because we can operate in the syndrome domain. But comparing to DBD, the performance is quite a bit worse. That is, we usually have more than 1 dB of degradation. So then we naturally want to ask, can we do some can we make some new novel decoder such that we can enjoy the benefits from both sides? And we want to have low complexity, but also good performance. And this line of research is called the soft-aided decoding or the hybrid decoding. And many works have been devoted into this topic. And we have proposed one decoder called the Dynamic Reliability Score decoding for product codes, and they give very good performance. And we want to, in this work, we want to adapt the DRSD for general product-like codes. So now we propose this for the plain product codes, but now we want to extend it to see if we can do it for the general case. And for example, we will use OFEC code and staircase code because they are the most prominent example in this code family. Now let's dive into the details. We can look at the decoding of product codes, the iterative decoding. With the example of the plain product code, it is arranged in such a 2D array such that every row in the column is protected by a component code decoder, a component code, and they are usually equipped with a low complexity algebraic hard decision decoder. And then we can decode them this way that we first decode all the rows, then decode all the columns, then the rows, then the columns, and we can do this iteratively. And you can see, for example, this bit is decoded by this row and this column all the time. And then in total, this is iterative decoding, and the message passing happens between the row and the column component code decoder. Then we can also try to get better performance by optimizing the code structure. So we can extend it. For example, if we use a special coupling, we can build a staircase code. And you see this block is similar to a product code, but in this case, we take two neighboring blocks such that this is a component code. And then we add another block, this is a component code, and so on. And we can do this for infinite lengths. And this is the staircase code. Another example is the OFEC code. as it's an important code, I will spend some time explaining the structure. The OFEC code use the component code, which is a extended BCH code. So the block length is 256 and is 2 error correcting. Extending means that instead of minimum distance 5, we will have minimum distance 6 by using this one extended bit. And this gives us some additional advantage is if we now consider some erasures, the increased minimal distance allows us to correct one additional erasure. Then we look at the structure. This is also a spatially coupled code, and you can see this as an infinitely long buffer. And every time we can add a row of blocks like this. And then we look at each row. It is 8 blocks. Here I only drew 4, but I skipped some such that the figure can fit in. And this is every block is 16 by 16. And every time we can add one, then this is we can do this continuously. And how do we build the component code? You can look. We can divide this 256 bits of this component code, this extended BCH code, into 16 small pieces. And the blue parts we draw as the front part, and the green part we draw as the back part. For the front part, we take some columns in the little blocks. So here we take one column, then here one column, and so on. This is 8 of them. And then we take those 8, and each of them we take a row. And put them together, we have 256 bits. And you can see that every time we can add one row of blocks, then encode the using the extended BCH code. Then in total, we can decode this with a sliding window decoder. So we can choose some window lengths, then decode them using the same kind of decoder that we introduced for the product code, the row component iterative decoder. And then this will be the OFEC code. So now we can talk about the proposed decoder, the dynamic reliability score decoding. And we will have the initialization part and the iterative decoding part. In the initialization, we will assign some dynamic reliability score and store them in the register. And these scores, they are introduced as a way to represent and update the soft message in a low complexity way. And then instead of only doing the traditional hard decision, we will now introduce some erasures. And then in total, we will need to use error and erasure decoding instead of the BDD, but you will see that EAD is very similar to BDD. Then we also want to introduce the miscorrection detection, which works with EAD together. So this pair, which forms the complete component decoder, is the main reason that we have better performance than IBDD. And overall, the DRS, we make them such that we can update them with hard information. So they are only increased or decreased, but without a specific magnitude. So we just use the 1. And then with error erasure decoding, we need ternary message passing. So this overall is a ternary message passing decoder. So we will have a significant complexity reduction compared to the TBD. Now we can look at each part of the decoder at the initialization. If we consider this example channel model, we can consider the BPSK modulated signal transmitted over binary input AWGN channel. And then the output PDF will look like this. And traditionally, we make a hard decision here such that if we receive a value with a positive value, then we say the transmitted bit is 0. Then you can see at this boundary, it's more likely that we make a mistake with the decision. This is why we want to introduce some erasures. That is to say, if the received value has a too small magnitude, we will not make a decision but mark it as erasure. And during the decoding, because we are based on hard decision decoding, if we have too many errors, it is very difficult to correct them. But if we have some erasures, you will see that we have some ways to correct the erasures during the decoding in an effective way. And another thing at the initialization is that we also want to assign the initial DRS. So we put those, we mark those bins with the different thresholds. Here I draw them equally, but they are also optimized for a specific code. Then you can see the received absolute value in this bin. They are assigned the reliability score 1, and this is 2, and so on. And the principle is just that the bits which are less reliable, they get lower score, and the bits that are more reliable, they get higher score. Then in the decoding, we use error and erasure decoder, which is different from the traditional error and erasure decoder. What we do is that we will make 2 test patterns out of the ternary received vector. So this Y here is a row or a column, and then it is binary plus some erasures in there. And then we cannot decode erasures directly, but we can replace the erasures by some random binary values. And in this case, we want to fill this with a pair of random binary vectors, and they are complementary. Complementary ensures that we are at least able to find we're always able to correct if the 2 times error plus erasure is within the minimum distance. This is why we want to have complementary. Then this random means that they are filled with different the vectors bits in each iteration. This means that we will have different code word candidates in each iteration. And this is beneficial because we will have eventually many candidate code words during the iterative decoding, even though every time we only do 2 BDD. And then how do we choose the code word candidates is simply by Hammond distance, so the one that is closer to Y at the unerased position. Then we want to introduce miscorrection detection here in this unit. The reason that I will explain in a bit. First, I want to talk about some properties of this error and erasure decoder. As I said, we are guaranteed to decode up to minimal distance, just as BDD. But also, because we are doing some guessing here, it is possible that we go beyond the minimal distance. But also, we have increased miscorrection rate. That's why we want to introduce the miscorrection detection. And from the complexity point of view, at the beginning iteration, when we will have some erasures, that's why we need to have this 2 decoding paths. So we will have more BDD executions than in the hard decision decoder in the IBDD. But once the erasures are resolved, EAD just becomes BDD. Then in the later iterations, the complexity is similar as in IBDD. Then it is also possible to not fill the erasures with 1 pair of filling pattern, but more, like J pairs. And if we can afford more complexity, we can do this, which will also provide some more performance gain. Then we talk about the miscorrection. So what is the miscorrection? When we talk about miscorrection, we are looking at the component code, and in our case, the BCH code. And in the code that we are typically used for optical communication system, the component codes are usually BCH codes with high rate. And miscorrection is most prominent problem for those high rate codes. It happens when we receive some vectors, say Y, then we decode them, then we say find the code word W, which is indeed a code word because it belongs to the code book that we can check with the serial syndrome. But then we realize that W is actually not the X, which is the transmit code word. But the component code will not be able to know because it doesn't have any knowledge about this. It only knows that it found the code word. And this happens because our component code have a high rate, then the code words are close to each other, then it's quite possible that we, with some more errors, then we are closer to another code word than the transmitted code word. And when the code words are very far apart, when we have slightly bigger minimal distance, we are more likely to have a decoding failure than having such a miscorrection. But this is it happens if the minimal distance is rather small. For example, as 5, 7, or 8, this problem is quite prominent. And you can see that once such a miscorrection happens, for example, for one thing, the current component decoder will not be able to see there are still some errors because it will be protected by a zero syndrome. And then we introduce more errors because we did a miscorrection, and then this error will also propagate during the iterative decoding. That's why it significantly impairs the hard decision decoding performance. And then the DRS was introduced to try to provide a solution to the problem of miscorrection. The details about how to calculate the DRS during the decoding is given in our previous paper in this algorithm, and I will not go into details in this presentation, but I want to just give an overview that the DRS, as we saw earlier, was initialized with the soft channel information, and then we update them with hard messages, so they are increased or decreased during the decoding by some specific rule. And then we use a simple observation that if we make a BDD decision, then if it tries to flip a bit, which we think is highly likely to be correct, then this BDD decision is very likely to be a miscorrection and should be discarded. And this is how the soft information is helping us to improve the hard decision decoder. Then we see that together with EAD, which is producing many different candidate code words during the iterative decoding, and then the miscorrection detection filters out the wrongly decoded code words. Then eventually we should reach the correct code word that was transmitted. This is why the performance is better than IBDD. Okay, now before we look at the final results, I want to mention the way of optimizing the parameters of the decoders. So I talked about thresholds a lot. We have different thresholds for erasures, for the ERS, and for miscorrections, and they should be optimized for a specific code if we want to have the best performance. But grid searching will be time consuming. Then we realized that we can try to use some hyperparameter optimization tool. For example, we use this Optuna, and then I briefly talk about Optuna. So it works this way. We will give the Optuna some initial decoder parameter theta, which contains all those thresholds. Then we put it into the decoder, and the decoder calculates a threshold SNR such that the post-decoding bit error rate is below 1 to the power of -4. Then it gives this threshold SNR to Optuna. And Optuna is a Bayesian hyperparameter optimization tool. It tries to estimate what should be the next set of parameters to sample such that it can get the most information from the next threshold value. Then it do this in the iterative way till it think it has gained enough knowledge about the behavior, how the decoder parameters affect the decoding performance. Then it gives us the best optimization hyperparameters that it thinks. This is how we optimize the thresholds. Now we can look at the result. We simulate for the OFEC code. We look at the reference, the soft decision decoder, the TPD, which is decoded with 3 soft iteration, 2 hard decision iteration. Then the soft decision uses 42 test patterns. And we also look at IBDD with 20 iterations. And the performance is quite a bit worse, and you have a high error floor here. And then we can use DRSD, which gives us a very good improvement in the waterfall region. Here I use different J. So one means we use just one pair of filling pattern. So this is the EAED. Then if we use a bit more BDD steps, then we can get better with 2 and 3 pairs of EAED. And then we see that there's a problem with the error floor, even though it's already lower than the IBDD, but it's still not as good as we like it to be. But luckily, we found out that it's the minimal stop pattern that is causing this kind of error floor for us. So minimal stop pattern, if we look at the plain product code, for example, 2 error correcting, then if we have 3 errors in each row and column, then decoder will stuck because it is 3 is beyond the decoding capacity, then it's not able to move on. And for the OFEC code, it's also 2 error correcting, and even though the code structure is different, but if we do some rearrangement, then we see this kind of minimal stop pattern is still the main problem. But solving such stop pattern is not too difficult, and this has been done in different literatures. The principle that we do here is that before the last decoding iteration, we can record the bits that were constantly having decoding failure. Then we flip them, then we do one last iteration to clear them out. Then eventually we can solve this error floor problem here. And then in total, we have 0.9 dB of gain compared to the hard decision decoding. Okay, then we can also look at the example with a staircase code with 3 error correcting BCH code. Then we compared with some state-of-the-art soft-aided decoders. So these are different decoders that was proposed. And this is the hard decision IBDD. And you see the DRSD behaves the best among the soft decision decoders. That was the content of my presentation. We have proposed a generalized low complexity hybrid decoding scheme for product file codes. And we show with numerical simulation results that the performance improvement is big compared to the traditional hard decision decoding. And we use a Bayesian hyperparameter optimization tool for those codes such that we can easily optimize all the thresholds that was needed. And if you have any questions, feel free to contact us. And I thank you for your attention. This is all of my presentation.